guys, welcome back. So in our previous video, we looked at logarithmic functions. We introduced them, talked about some of their basic properties, but we mainly focused on how they relate to our exponential functions in that inverse relationship. Now we're going to start looking at some more properties of just logarithms. Our first property is called the addition property of logarithms. If I've got log base b of m times n, this can be expanded as log base b of m plus log base b of n. And that's why it's called the addition property, because we're expanding that using addition. So our first example, write the logarithm as the sum or difference of logs. That's what your textbook's going to say. That's what your test is going to say. But essentially, that just means to expand that logarithm. Log base 6 of 7 times 11. Since these terms are being multiplied, we can expand using addition. This expands to log base 6 of 7 plus log base 6 of 11. Make sure you guys are including your base when you're rewriting logarithms. It's not optional. You have to write it. If you remember from our last video, if there's no base there, it's understood to be 10. So be careful, make sure that you have a base written if it's not 10. Anytime you end up with a log expression that's only involving numbers, so both of these are examples of that, log base 6 of 7, log base 6 of 11, you want to see if you can simplify that any further. We evaluate a logarithm by trying to figure out what the exponent is. So 6 to what power is 11? Well, I can't think of one, neither can you probably, because there isn't one. Not a nice, pretty number anyway. But anytime you see expressions that are like that, you want to try to simplify, because obviously, and we've seen this before, we always have to simplify as far as possible. Log of 100x. Now here, because we don't have a base written, it's assumed to be a base 10. Since 100 and x are being multiplied, we can expand using addition. So it's log of 100 plus log of x. Now in this first expression, we see that we've got just numbers involved. We do have a base of 10 here. And if we think about this, 10 to what power is 100, we can simplify that. 10 to the second power is 100. So log base 10 of 100 is equal to 2. So we can expand this to 2 plus log of x. Our subtraction property of logs involves a log that starts like this, log base b of m divided by n. When our argument is a ratio, then we can expand using subtraction. Log base b of m minus log base b of n. Because we're now converting to subtraction, we need to make sure that we take the order into consideration. It's always the numerator minus the denominator, because subtraction is not commutative. You can't just change the order and have it be the same thing. Log base 8 of 23 over x. We expand division using subtraction, so log base 8 of 23 minus log base 8 of x. This first term, we want to make sure that we can't simplify it any further. Can we find an exponent that when we raise 8 to it, we get 23? Nope, so this is simplified. The natural log of e to the 5th over 11. Expanding this division, we have the natural log of e to the 5th minus the natural log of 11. If I look at this expression, again, my base here is technically e, isn't it? If you want to add that in, please go ahead, but make sure that you're aware that it's not going to be present there. You need to know that it goes there if you want to add it. And e is that 2.71828 number. So are we going to be able to find an exponent that when we raise e to it, we get 11? Probably not. Let's look at this one, the natural log of e to the 5th. Those inverse properties that we saw in our previous video are now coming into play. Again, we have a base of e, natural log of e to the 5th simplifies to 5. Again, that's our inverse property. To write it over here, we had the natural log of e to the x equals x. That was from our previous video. And if we look at the similarity and how they relate, natural log e, the x is 5 in this case. The power property of logarithms says that log base b of m to the n, that exponent on our argument can be brought down as a coefficient. So log base b of m to the n is equal to n times log base b of m. Now I want to quickly look at something. What's the difference between log of x squared versus log of x squared? In this first one, the square is only on the base of x. On this one, because we have parentheses on log of x, this is actually equal to log of x times log of x, which doesn't follow our power rule for logarithms. This one, since our argument is being squared, we can bring that exponent down. This is 2 log of x. Now, another way we could look at this, I just thought of this. Log of x squared is the same as log of x times x. How can we expand multiplication? Using addition, this is log of x plus log of x. And now we have like terms which we can combine. 2 log of x. So there's another proof of that power rule. I love when those things come to me. It's great. Log base 6 of 3 to the 9, because my exponent is on my argument, I can bring it to the front as a coefficient. This is 9 times log base 6 of 3. Again, whenever we have a logarithmic expression that's just dealing with numbers, we want to try to simplify. 6 to what power is 3? Be very careful. It's not 1/2. That's the same thing as a square root. So the square root of 6 is not 3. We can't simplify this any further. The natural log of the cube root of x. I can rewrite this as x to what power? The cube root of x is equal to x to the 1/3 power. We reviewed that rule for converting from radicals to rational exponents in our last video. And now our exponent can be brought to the front as a coefficient. So this is the same as 1/3 natural log of x. Log of x plus 4 squared. Again, because our exponent is on our argument, we can bring it to the front as a coefficient. This is 2 times log of x plus 4. But this expression, log of x plus 4, we can't do anything with it. We don't have a rule that allows us to expand addition. This is just going to stay the way it is. Log base b of x to the 4th times the cube root of y. So now we're seeing a combination of rules. The first thing that we see is that we've got two things being multiplied, and we can expand the product of two things using addition. So we have log base b of x to the 4th plus log base b of the cube root of y. Now in this first term, our exponent of 4 can be brought to the front as a coefficient, so 4 log base b of x. And in our second term, we can rewrite the cube root of y as log base b y to the 1/3. And now that exponent can be brought to the front as a coefficient. If you recognize that the cube root of y is the same as y to the 1/3 and you don't want to take this intermediate step, that's fine. But for some of us, we want to make sure that we review that rule of converting from radical form to an rational exponent. log base 4 of the cube root of x divided by 16 y to the 4th. So again, the first thing that we see is that we're dividing this by this. And how do we expand division? Using subtraction, log base 4 of the cube root of x minus log base 4, 16y to the 4th. Now, this first expression, the cube root of x, we know that that's the same as x to the 1/3. So this whole thing, kind of acting like an exponent, is going to come to the front as a 1/3. So we have 1/3 log base 4 of x. Now, in this second expression, we see an exponent of 4. Can we bring that 4 to the front as a coefficient? And the answer is no, because the 4, this exponent of 4, is not an exponent on my entire argument. It's only an exponent on the y here. So it's not an exponent on 16. But we can see here that we've got two things being multiplied, and we can expand that using addition. Since I'm subtracting this entire logarithm, I need to subtract its entire expansion, which means I'm going to use parentheses when I rewrite this. Log base 4 of 16 plus log base 4 of y to the 4th. The parentheses are keeping that entire expression of log base 4 of 16y to the 4th together. But I can distribute that minus sign to get rid of the parentheses. Minus log base 4 of 16 minus log base 4 of y to the 4th. Now this exponent of 4 is on my y, my entire argument, so I can bring it to the front as a coefficient. And I also want to look at this log base 4 of 16. Anytime you've got just numbers involved, you want to see if you can simplify. 4 to what power is 16? Well, 4 squared is 16, so this expression is equal to 2. And this is our expression written as the sum or difference of logs. So when we're expanding, we can follow a certain order that will help us in making sure that we get our answer correct. So I recommend expanding in the following order. Expand division first. Division's going to expand to subtraction. Then expand multiplication. And be careful, if you're expanding multiplication after a minus sign, you need to use the parentheses like we saw in that previous example. And then the very last thing that you can do are the exponents, where you bring your exponents down as coefficients. You're going to find that in certain problems, the order's not going to make a huge impact, but if you can follow this order every single time, then you'll be better organized when you're following your work, especially when you're just starting out practicing these types of problems. And now we're going to go the other way. So we just expanded. Now we want to take this expanded form and condense it. So the directions read, write the expression as a single logarithm. If it's a single logarithm, the word log or the natural log, that ln, is only going to appear once. It's one logarithm. So if we expanded going division, multiplication, exponents, if we're going the reverse route, we're going to follow that order in the reverse route. So the first thing we're actually going to do is get rid of our coefficients, which is what we were talking about when we expanded the exponents. The exponents came down as coefficients. So now when we're condensing, we're going to take our coefficients first and make them all exponents. Then you want to condense any addition. Remember, the second step when we were expanding was the multiplication, which became addition, so we want to condense any addition. And then last but not least, hopefully at this point we only have two terms being subtracted. And our last step will be to condense that subtraction using division. So let's look at some examples. Log of 25 plus log of 4. Since these two are being added, we condense them using multiplication. This is log of 25 times 4, which is log of 100. Since the base here is understood to be 10, we actually do have all numbers involved, and we need to try to simplify. At this point, we've seen this particular expression several times. 10 squared is equal to 100, so log of 100 is equal to 2. Log of 7x plus 6 minus log of x. Since our two logarithms are being subtracted, we condense using division. The first argument becomes the numerator. The second argument becomes the denominator. Two natural log of x plus 1/3 natural log of x plus 5. And we have that same little icon here, so I'm going to rewrite this. Plus 1/3 natural log of x plus 5. If we look at the order, the first thing we want to get rid of or undo is our coefficients. So our coefficients are all going to become exponents first. So we have the natural log of x squared plus the natural log of x plus 5 to the 1/3 power. If you want to write that rational exponent as a radical and make it the cube root of x plus 5, that's a-okay, but you can leave it as a rational exponent as well. Now we want to condense any addition, which are these two, and we condense using multiplication. So this is the natural log of x squared times x plus 5 to the 1/3 power. And you can leave it just like this. So you can see we're starting to add more and more steps into these examples. 2 times log of x minus 3 minus log of x. Again, we always start by making our coefficients exponents. So this is log of x minus 3 squared minus log of x. And then we don't have any addition to condense, so we skip to subtraction, and we condense subtraction using division. So this is log of, the first argument is the numerator, x minus 3 squared. The second argument becomes our denominator over x. One-third log of x minus 3 log of 4 minus 8 log y. Coefficients are first. So we have log of x to the 1/3 power minus log of 4 cubed, which we will eventually simplify that, minus log y to the 8th. Now, it doesn't appear that we have any addition here, but if you look at these last two terms, what do they both have a factor of? They both have a factor of -1. So we're going to actually factor that out so that we can see where the addition is in this problem. If I factor out that negative, we're left with log of 4 cubed plus log of y to the 8th. And now we can see that we can condense these two terms in the parentheses using multiplication. Four cubed is 64. And now we always want to end with just two terms being subtracted, if any subtraction, and then we condense using division. So this is log of x to the 1/3 divided by 64 y to the 8th power. This is not right. This should be 48. Let me fix this. Sorry, guys. I wonder if anyone would have caught me on that mistake earlier. Is that... No, wait, I'm sorry. I'm still wrong. Maybe I was right. I was right. This should have been a 4. I was right all along. I started second guessing myself, guys. This is 64. I'm sorry. Sorry for the issues. I was just working with exponents today too. So anyway, now it is correct. It was correct to start with, and then I second guessed myself, which we can see doesn't always really work out in our favor. So stick with your gut instinct when you're on a test. That's your public service announcement for today. The change of base property allows us to evaluate any logarithm using our calculator. In our last video, we, very sadly discovered that we can only use our calculator to evaluate base 10 and a natural log. The change of base property allows us to evaluate any logarithm with any base. If I've got log base b of m, so any base, any argument, this can be written as log of m divided by log of b. This is also equal to the natural log of m divided by the natural log of b. In both of these ratios, we've changed the base of our logarithm. In the first one, we've changed it to a base 10. In the second, we've changed it to a natural log, a base e, which we can use both of these to, or we can use our calculator to evaluate both base 10 and base e. This is a really awesome property. I'm interested to see how you guys figure that you can use the change of base property, aside from the questions that obviously say, use the change of base property to evaluate. It's even more useful than just in those problems. So evaluating log base 5 of 347, using the change of base property, this is equal to log of 347 divided by log of 5. Or you can use natural log, the natural log of 347 divided by the natural log of 5. It doesn't matter which you use, natural log or base 10 logarithms. I tend to use natural log, and you're going to see that I favor natural log even as we go through solving equations. But that's because when you move on in math, if you start taking calculus and moving through that sequence, natural log comes up a lot more frequently than base 10 does. So I just got conditioned to using natural log over base 10, but either one works. So go ahead, use your calculators and try to evaluate these ratios. The one thing I'm going to make sure that you guys are cautious of when you're typing this into your calculator, you want to make sure that you have parentheses around your numerator and your denominator. Okay, just make sure that that's there. Some calculators, it might be easier to evaluate the numerator by itself and the denominator by itself, record those decimals, and then divide those two decimals. It just depends. But see if you can get this answer. And if you are having trouble with it, again, bring your calculator to class and we'll look at it one-on-one and make sure that you are comfortable evaluating using change of base. But you should get approximately, I don't know. I don't have a calculator with me. So you guys tell me what the answer is and we'll talk about this next time in class. Sorry. So the properties that we learned today were our addition property, our our addition property, our subtraction property, and our power rule for logarithms. And then we also learned about the change of base. Knowing how to expand and condense logarithms is going to be essential when we start solving equations using involving logarithmic expressions. So please make sure that you practice these. Practice is going to make perfect here, guys. I've seen it time and time again where we only kind of glaze over these ideas, but It's really important, so please make sure that you guys are comfortable with these properties, especially those complex examples like we saw at the end of each of those sections. So we'll see you guys next time for solving exponential and log equations.